I'm Jun Chen, Content Assistant Professor and Department of Bioengineering at UCLA. Today, I would like to share with you a story entitled Smart Textile for Personal Healthcare. So why we need a personal healthcare? So look at this curve. It describes the relationship between disease burden and the cost. So our current healthcare system is based on typical intervention. That means, for example, if you have a headache, then you can call the doctor, then doctors will check his or her schedule, and then you can make an appointment, and then you can maybe 2 days later, you can drive a car to the clinic center, get some treatment. You can say this is the current healthcare system is based on the disease management and is very high cost because we need more money to get back to our health, and also is very low efficiency because low efficiency means it has very low doctor-patient efficiency. So usually we need to drive a long distance to the clinic center, and we still need to wait for 2 days. Before the driving to the clinic center, and also after you arrive at the clinic center, maybe the doctor just give you 10 minutes treatment and monitor your body temperature if you have a headache, this kind of treatment. So you can say this is very low doctor-patient efficiency. So we have been thinking about if we can perform at least the earliest molecular detection. For example, if we have our body temperature sensor, which can continuously monitor our body temperature. If there are found some abnormalities, then we can share those information with a doctor over distance by use email or phone call or even text message. So then they can give me immediate care. So this is the concept of personal health care. It's based on the health enhancement and the disease prevention. So it definitely has a higher quality and a low cost because we don't need to go through this kind of headache, this kind of bad feeling. So maybe after the doctor check your profile set, or maybe you just take some good rest and drink some hot water, maybe this kind of headache or this kind of will not come to you. So this is the concept of personal health care. Although we can say one of the key challenges that is to realize this type of healthcare transformation, that we need low cost and also wearing comfort those biomedical devices and to continuous monitoring of physiological information. With those kind of continuous monitoring, we can enable the change of current reactive and disease-centric healthcare system to a personal mode, which are focused on the disease prevention and health promotion. But how to develop those low-cost, wearing comfort biomedical devices could be another key challenge to realize this kind of healthcare transformation. So Apple Watch is one of the famous wearable biomedical devices which continues monitoring. For example, when you wear this type of watch, you can read out your heart rate continuously. But definitely this type of devices has a certain disadvantage. For example, this additional burden to wear. So especially a lot of these people sit in the office a long period of time. So if you're typing on a keyboard and you wear a watch, definitely it's very inconvenient. And also it's very expensive. So actually, textiles is a piece of indispensable component of our daily life. So everybody was supposed to wear clothes and go to work. Textile actually has a long history of human beings. Textile itself has a number of advantages or features that could be developed into wearable biomedical devices. For example, they have a wide range of materials choice, from natural materials for them silk, wool, cotton, to synthetic material for peptide, polyimide, polyester. All of those materials actually is able to be developed into textile form. And also many of them are biocompatible, biodegradable, even bioabsorbable. That means these have a lot of advantage to be developed into biomedical devices. So, but all of those materials I mentioned here, actually, no matter it's natural materials or synthetic materials, they are chemically inert and they are not conductive. Actually, it's very hard to develop those type of materials into wearable biomedical devices for continuous monitoring. So how to develop textiles into biomedical devices? actually there comes a lot of challenge to realize this kind of healthcare transformation. Actually, human body contains a lot of biomechanical motions. For example, when I talk to you, my mouth moves up and down. Actually, my finger, for example, when I perform the hand gesture during the lecture, actually my finger moves a lot. And also our heart is keep beating all the time, or our breathing. This kind of biomechanical motions actually is ubiquitous in our human body. So I have been thinking about, can we develop different type of textile products which can convert those biomechanical motions into electricity? If we could do that, actually those generate electricity contains a lot of frequency and amplitude information. So those information could use to mirror the biomechanical motions for diagnostics or for sensing performance, for sensing applications, or even for some other application scenarios. So with these concerns, recently we developed different type of biomedical textiles to realize this kind of a personal healthcare. So typically we have three type of application scenarios. One is biomonitoring, a second is could be for therapy, a third is could be energy. So why energy is a portion of those personal healthcare big picture? That's because for some of the biomedical devices, they certainly need energy to drive them, need the power to operate them. So with this concern, if we could use some textiles generate electricity, then they can help to provide sustainable power supplies to those biomedical devices. So let's first look at the sensing part. So how can we use textile for biomonitoring? So the very first application scenario I want to share with you, that is we want to use textile for sleeping quality evaluation. Actually, sleeping disorder is a major health threatening in high-paced modern society, especially in US, and which could result in mood disturbance and many heart-related diseases. So the current technology for sleeping disorder monitoring, for example, we have polysomnography. So during sleeping, you just use a lot of wells and to wrap up around human body. You still need a clamp to clean the fingers. And another application technology that is used the cell phone app. So you during sleeping, you just put this bulky cell phone on your bed sheet. So if your body move a little bit, so this type of body movement could be detected by cell phone app. So you can say those technologies certainly has a number of shortcomings. First, they have very complex structure design, and second is very high cost. For example, for those technology looks like very high tech, and still even a cell phone is Apple cell phone that definitely need about $1,000. I know, and you still need additional app fees for those diagnostic apps. So you can see definitely it's a high cost, and also it's very inconvenient to use. So for those wells, this polysomnography, this kind of sleeping disorder monitoring technology, maybe will make your sleeping disorder worse. And also is not enough accurate. For example, for this bulky cell phone app, sometimes it's very hard for it to detect the body movement during the sleeping. So with this concern, we recently developed a pressure-sensitive large-scale small bed sheet. Look at here. Basically, this is a typical bed sheet, but the bed sheet, we have a number of sensor ring here. So each of sensor is very sensitive to detect applied pressure and generate electricity. So those generate electricity will go through a number of circuitries with the single amplifier, and also we have the ADC analog to digital converter, and eventually we can use this kind of Bluetooth and this kind of microcontroller to wirelessly transmit those generated electric signal to the cell phone app. Then with those kind of electric signal generated by these sensors, then they can detect the body movement during the whole night sleep. But this kind of a three-layered structure actually is not waterproof, and also sometimes for those batteries need to be washed. So with these concerns, recently we developed another single-layered ultra-soft washable smart textile for this kind of sleep apnea prevention. So look at a device actually is the scale bar is 1 meter. You can see the device could be large scale fabricated. If we take a close view, one section of the unit, you can see basically is a number of functional fibers which is interlaced or inserted into a commercialized fabric to form this kind of pressure sensitive smart textile. So when we cover this smart textile onto our belly, so during a regular breath, you can see that generate this kind of regular voltage signals. So once people have sleep apnea, that means when he or she stop breathing during the breath, during the sleeping, you can see they will generate a large fluctuation in the output signal. So we can develop this kind of large fluctuation into a warning signal. It's going to be either developed into a phone call or developed into a message, and then they can notify the family member immediately to wake him or her up. Otherwise, it's a cause to death. So this is a smart textile for sleeping monitoring. So we can either use them for sleeping disorder monitoring, we can use them for sleep apnea prevention. So actually, textile not only for do some sleeping related monitoring, they can use for possible monitoring as well. So here is one of the study. So we starting with this kind of fiber construction. We build up this kind of muscle fiber inspelled this kind of fiber. Then we can use this kind of electron spinning to form this kind of long wavelength structure. So this type of long wavelength fabric is also very sensitive to the biomechanical motion. For example, when we attach this device to leg arteries, so before and after exercise, we can see the heart rate is increased from 73 per minute to 92 per minute. So basically, this piece of devices is very small, just with has a size of 1 centimeter by 2 centimeters, and with a thickness about only 8 micrometers. So it's very thin. So look at here, it can continue to generate those kind of current peaks. So we just calculate the peak numbers and divide it by time. Then we can know the heart rate continuously. And this long woven textile actually is lack of wearing comfort because it's lack of breathability. So recently we really developed a piece of textile with construct based on the fabric. Look at here, we just take this kind of silver coated fabric as a substrate. On the top of them, we have this kind of flower shaped functional fibers. So how does it work? So basically, when we weld this piece of textile against our leg arteries, this kind of blood vessel expansion and compression will induce mechanical deformation between these functional fibers, for example, the polyester and the metal yarns. Then with the result, they can convert this kind of vessel compression or expansion into electricity. So by analyzing this general electricity, we can continuously read out our possible profiles and in a cell phone app. So in the future, we just wear this piece of textile to wear against, no matter it's on against the check artery or west artery or some other artery sites. So after we just take out our cell phone app, then we can continuously look at read out our possible profile. If we found some abnormalities, then we can share those data with the doctor over distance immediately. Then they can give us immediate care. So then this can help us to prevent some cardiovascular diseases. So actually, those type of one of the challenges for this kind of wearable biomonitoring devices, that is a motion artifact, because during the body movement, they can also give some mechanical excitation to the devices. So those type of biomechanical motions, human body movement could also generate electricity. Those could be introduce some noisy noisy signal to the monitoring signal. So with this concern, recently we developed a cardiovascular monitoring devices which could monitor our possible profile even with body movement. Look at the design. Basically, we have a super hydrophobic coating layer to make a device waterproof. And in the middle, we have carbon nanotubes that is coated cotton yarns, cotton fabric. And then we have FEP as another triballic layer. We have the aluminum layer as electrode. And then eventually we get this type of textile-based cardiovascular monitoring system. So we introduce this kind of machine learning algorithm to help to reduce the motion artifact. So with the help of this machine learning, we can see that this type of devices can monitor our blood pressure even with body movement. So and this type of monitor result also validated by this commercial standard cardiovascular hospital set this kind of equipment to see that actually the measurement result is accurate and actually could be comparable with this commercialized cardiovascular monitoring system. So basically, in the future, we'll just wear this piece of textile against our vessel arteries, So even we have body movement, then we can still continuous read out its possible profiles and to perform this kind of continuous cardiovascular monitoring. So that is some examples for biomonitoring with textiles. Textiles can also utilize for therapeutic applications. So here is one of the example. We just want to use textile as a assistive physical therapy. Actually, 37.5 million Americans 18 or older report trouble hearing, and almost 75 of them are unemployed due to the lack of effective communication tools. Even you don't understand American Sign Language, so it's very hard for you to communicate. So with this concern, recently we developed our text glove, which could perform this kind of wearable center-speech translation. It has two components. One is stretchable sensor unit, which is responsible to convert this kind of finger biomechanical motion into electricity. Then we have a wireless flexible PCB, that's printed circuit board, which is responsible to do the singular processing and the transmission. So here is a working principle. We just take one stretchable sensor unit for electrician to show how it's convert this kind of finger spelling biomechanical motion into electricity. Basically, this kind of stretchable sensor unit has a cool shell structure design. We take a rubber fiber as substrate. We have polyester and a metal hybridized fibers to twist against the rubbers, and we have a PDMS or the outermost shell. So when we weld this type of stretchable sensor unit against fingers during this kind of finger spelling, we can see the stretchable sensor unit will get stretched and released during this kind of mechanical motions. They will induce a contact separation between this kind of PDMS and the polyester. With the result, they will generate electricity in the internal circuitry. So here, when we weld this stretchable sensor unit against our 5 fingers, so we can see when we perform a standard American Sign Language to express the letters, for example, ABC, the numbers 1 to 3, or short phrase, for example, I love you, to show this kind of fundamental language component or element. We can see those are generated actually singular accordingly during this kind of finger spelling. So with analyze those generate electric singular patterns, we can perform this kind of center-speech translation. So when we wear these text gloves and perform American Sign Language, then you can see the voice and could be paid out by the cell phone app. So basically, when we perform this kind of hand spelling, so you can see those kind of hand gesture and generate electricity singular could be displayed on a cell phone app for timely wearable center-speech translation. So this work, here is a video I want to share with you. Look at here. So before that, let me check if to make sure I'm sharing the computer sound. So
I L Y.
So basically, in the future, when you just wear this towel gloves and then bring cell phone, then you can translate your this kind of American Sign Language into speech and into voice. Actually, this kind of voice could be also translated no matter in English or in Chinese or in Japanese or in any of the language type is possible. So recently, this work received more than 200 median coverage in NPR, ABC, CNN, and also is highlighted by Science, and also is recognized as the top 10 science story of 2020, and also is also made the top 100 the 2020 automatic top 100 articles among their 3.4 million works that is across all the subjects in 2020s. So that is one example of therapeutics. So actually textile can also apply for energy applications. So look at here. So those are the wearable circuitry for biosensing. And here is a wearable ultrasonic sensors for heart rate monitoring. So definitely for those future wearable biomedical devices, they need power to drive them. So it's beyond the capability of a current battery system. You can see batteries, they have very rigid structure, and then they have made of toxic element, and also is very bulky. So it's very hard for you to incorporate those batteries into this wearable biomedical device system for continuous biomonitoring. So with these concerns, actually everybody is back to work well close and then go to work and go to street, as actually we have a number of renewable energy sources available to textiles. For example, we have solar radiation and mechanical deformation. If we could use textiles to harness those type of renewable energy sources, then we can use them to sustainably drive those wearable biomedical devices. Then we can get rid of this kind of a bulky and rigid battery system. So here is one of the design. Basically, we build up a hybridized power textile, which could simultaneously harvest energy from biomechanical motion and solar radiation. So it has two components. So triple electric textile is responsible to convert biomechanical motion into electricity. For this kind of solar textile is responsible to convert the solar radiation into electricity. So we have experimental data results shows that with a size of 5 centimeter by 4 centimeter, so the textiles could sustainably deliver power output more than 0.5 milliwatt with a wide reading loading resistance from 1,000 ohm to 1 meg ohm. So with this capability, we show that these textiles could be sustainably charge a cell phone and also to drive this kind of electronic watch. Actually, there's no battery inside. We just use this piece of textiles that they can generate electricity to sustainably operate those electronic watch. So actually, textile cannot only be harnessed to harvest energy from biomechanicals and biomechanical energy and also solar energy. It can also harvest energy from body heat or biochemical energies, for example, the glucose in the perspiration. So you can say with those different textile form, we can perform smart textile for electricity generation. So recently, I was invited to write a review for chemical review talking about textile energy harvesting technology. If you are interested to read this chemical review paper, it's entitled Smart Textile for Electricity Generation, and also is also made the front cover of the journal. So actually, energy harvesting textile has a number of challenges. That's, for example, we wear this solar textile and walk into shadow. There's no sunshine available, so the output will be largely reduced. But for small electronics or those wearable bioelectronics, they certainly need sustainable power supplies. So with this concern, recently we hybridized a fabric solar cell with fabric batteries. So basically at a photo charging stage, so they generate electricity. Those electricity could be sustainably stored, could be sustainably generated and then stored in a fabric batteries. So at the discharge plateau of this fabric batteries, no matter you twist the fabric or walk into a shadow or there's a rainy day, so you can see at the discharge of fabric batteries can stably have deliver electrical power. So basically with a regulating capability of fabric batteries, so this fabric could be used as a sustainable and a stable power source for viable biomedical devices. So today's lectures, I basically just give you a number of examples to show that we are using the nanotechnology, bioelectronics to develop different types of textiles for biomonitoring, for therapeutics, and also for energy applications. So let's come to a large part of our talk today. Basically, I would like to thank my wearable bioelectronics group at UCLA with a number of postdocs and PhD students, and also the collaborators and contributors, and also the funding agencies. So thank you very much for your attention, and I'm open to take any question, and welcome you to UCLA and Los Angeles.